Kia ora koutou, welcome to this next video of Science 1.1, Demonstrate Understanding of Aspects of Mechanics. In this video we are going to be looking at distance-time graphs. This is very common to occur in NCEA exams, that there will be a graph shown and we need to interpret the graph either by using calculations or describing the motion of something with the answers. We need to interpret a graph and write answers according to what the question is. So distance-time graphs, you'll see them with distance written on the y-axis and time written on the x-axis. So these distance-time graphs will describe the motion of an object. And so when we're looking at these distance-time graphs, we're going to need to use some new vocabulary when we're talking about what these distance-time graphs are showing. So if I've drawn a little, just pretend this is a section of road, finishes in a tree, just to make this a bit more aesthetically pleasing. If we had an object that was moving along the road towards a tree. So if we had a box here that moved partway down the road, let's say it moved 5 meters down the road, and while it was doing that, it wasn't, normally in real life this would start stationary and then it would accelerate. But what we're going to do is we're going to say that this, as soon as it starts moving, it moves at the exact same speed that it's going to go for the whole time. So we'll say that this object goes from there to here to 5 meters. Okay, and let's say that it takes 5 seconds to do that. So it takes 5 seconds. The object takes 5 seconds to move from 0 meters to 5 meters. So how would we show that on this distance time graph? Well, what we would see is that there will be an intersection point here. We'll see that the object goes from 0 meters to 5 meters. This would be 5 meters here. This is 5 seconds here. So it's going to, over a period of 5 seconds, the object has moved 5 meters. So we would show that by using a line that would look something like this. Oh, probably, here we go, near enough. All right. So we'd see a line drawn something like that. So this line tells us that the object that we're talking about has moved 5 meters in 5 seconds. So the vocabulary that we would use if we saw a distance time graph like that and we had to describe the motion of the object that this graph is showing, we would say that it's traveling at a constant speed. So for this section of the graph, the object that we're talking about is going at a constant speed. So it's not speeding up, it's not slowing down, but it is moving. It's not stationary. Yeah? So this is the object traveling at a constant speed. Now let's say that the object then stayed here. Let's say it stayed stationary for 2 seconds. Stays stationary for 2 seconds. So what would happen is that we've gone from 0 seconds, 5 seconds, 6, 7. So at this point in time, it'll now be at 7 seconds. How would we show on the graph that the object has moved 5 meters and then stayed still? How are we going to show that? So what's happening here is time is passing. So we've got 2 seconds passing. So the line will go like this. But because it's staying at 5 meters, it's not going to go up or down. It's just going to go from here directly horizontally to 7. So it goes like that. Whenever you see a flat line like this on a distance time graph, that is showing that something is stationary. So this is the correct vocabulary that you should use. So if something is staying still, the way we describe that in physics is that it is stationary. Okay. Now let's say for the remainder of the trip, so it's got 5 more meters to go. Let's say that it does actually start going a little bit slow. So it starts a little bit slow and then it speeds up right towards the end. So I tried to show that in fluent motion, but it didn't really work. So pretend it's starting stationary, and this is more realistic where it starts going slow and then it speeds up until it reaches the end. How are we going to show that an object is speeding up with this distance time graph? So this takes it 3 seconds to reach the 10 meters. So it's going to, well, we're going to get to a point here where it takes 10 seconds to get to the 10 meters. We could do a line like this, but that's showing that um, the object would be going at a constant speed. So the way that we show that it's speeding up is that we do a curved line like that, or it would be better than that if we um, had a bit more control. That'll do. So you can see how it's curved. So it starts off, the curve of the line shows how fast or the speed of the object. So this, if you see a line like this in a distance time graph, that is showing acceleration. Okay, so these are 3 bits of vocabulary that we need to know for this course. So we've got constant speed if something is moving at the same speed, stationary if something is no longer moving, and then acceleration if the speed is increasing. So we've got acceleration. You could see that the line in a graph could curve downwards, and that would be it's decelerating. So if we had something that, if this gradually curved down to become stationary, that would be decelerating. If the line was going in a straight line down to the bottom, then that would still be a constant speed, but that would be showing the object just going backwards towards the start. But really, these are just the 3 um, bits of vocabulary that we need when we're talking about distance time graphs. Next, what we need to be able to do with distance time graphs is to be able to use the values that we're given from the y-axis and from the x-axis, and be able to calculate the speed that an object is traveling. So we'll use this graph here. We can calculate the speed for something that's traveling at a constant speed, or something that's stationary. We cannot calculate the speed that something is traveling when it is accelerating, not with the information that we have. So we'll only be asked to calculate the speed of something that's traveling at a constant speed. So to do that, it's the gradient, so the steepness of this line, that tells us how fast the object is traveling. So to calculate the gradient of something, we need to go, it's the rise over the run. So gradient equals the rise divided by the run. So in other words, the gradient in this case, because the gradient tells us the speed, so the speed is equal to the change in the rise. So the change in the rise is the distance, change in the distance, divided by the change in time. So we might get a question that asks us, how fast is the object traveling for the first 5 seconds? Well, for the first 5 seconds, so if we had the first 5 seconds, t would equal 5 seconds. We would need to work out how far the object has traveled during those 5 seconds. So we'd look at 5 seconds, how far has the object gone? And we know that it's 5 meters. So distance, or the change in time, equals 5 seconds. The change in distance equals 5 meters. So we would simply put that into our formula here, where the speed, the velocity, is equal to the change in distance divided by the change in time. So that would mean we've got 5 meters. 5 meters divided by 5 seconds. 5 divided by 5 equals 1. So our answer for how fast this is traveling during the first part of it here is going to be 5 meters per second. 5 meters per second. Okay. we'll do another example. So let's say that when we were looking at this before, we said that it was accelerating. Let's pretend that it wasn't accelerating. We'll say that it was just traveling at a constant speed for the remaining 3 seconds. So the constant speed would look something like this. Well, I'll keep that there. So instead of saying it's accelerating, we're going to say that over the last 3 seconds, the object travels 5 meters. So it goes from 5 meters to 10 meters, and it takes it 3 seconds. So here it's slightly different because the values are not starting at 0. So we need to use this this formula again. We'll do the working over this side. So it's still the same formula. So velocity or speed, velocity equals the change in distance over the change in time. Here, the change in distance, so we'll go change in distance equals this 10 meters is where it finishes off, minus the 5 meters where it starts. So what we're interested in is what this distance is here. We're not going to use 10 meters because that is not the change in distance because it started at 5 meters. So to work out the change in something, we need to go the final value. So I'll just go final value minus the initial. L. So the final value is 10. 10 meters minus 5. So the change in distance is 5 meters. The change in time is 10 minus 7. So in this case, we're just looking at the change in time for this section here. So to work out the change in time, we go change in time equals 10 minus 7. So we're going to end up with 3 seconds. Okay. So now when we do our formula, we need to go velocity equals the change in distance, which is 5, divided by 3. So what does that equal? It equals, I had to use my calculator for this, which might be embarrassing, but who cares? 1.6. So 1.6 meters per second. Or you might see that written as meters per second to the power of -1, like that. Or even, we should round it up, 1.7. 1.7 meters per second. So that's about it for this one. So we've looked at how to describe distance time graphs using words, and then we've also looked at how to calculate the speed by finding the change in distance over the change in time. We can see here that this one, 1.7 meters per second, is a higher value than a greater value than 1 meter per second. 5 divided by 5 is 1. And that makes sense because it's the steepness of the line that tells us how fast an object is traveling. So we can see that this line is steeper than that line, so the object must be traveling faster during this section of the graph. So I hope that helps. That's distance time graphs. Like and subscribe for more videos. I'll see you next time. Thank you.